Hi, I'm Jose Esposito, one of the authors of this book. And people have been asking me a very important question, a very interesting question about the 1D system in compositional grading. In isothermal systems, you have to solve NC fugacity equality equations. But for the non-isothermal case, you have to solve NC minus 1 diffusive flux equations plus the equation of the hydrostatic load. Question is, why do you have to force the hydrostatic load restriction in the non-isothermal case, and you don't care about it when you're dealing with an isothermal case? Well, let's consider the equations here. You can see the isothermal system of equations there, right? It's only the fugacities modified by the gravitational field. Okay, in the non-isothermal case, you have the NC minus 1 diffusive flux equation is equal to 0, okay, JI equal to 0, and then you have to input the hydrostatic condition. Why is that? Right? Well, first of all, in the non-isothermal case, you reach a steady state. Yes, you reach a steady state, and when you reach steady state, diffusive flux are 0 and the fluid is at rest, but it's not in equilibrium. Fugacities, even modified by gravity, are not the same. But for the fact that the fluid is at rest, you have to input the hydrostatic restriction because the equations of the diffusive flux are not responsible for that. Well, okay, but why this is not the case for the isothermal system? Well, this is a very interesting question, because for the isothermal system, okay, if you have to solve these kind of equations here, you must know, first of all, that this set of equations here, they came from the same condition that the modified chemical potential is constant throughout that. d mu y is equal to minus molecular weight of component I g dz. When you substitute here the concept of fugacity and you integrate from the depth of reference to any other depth, you obtain this equation. So this equation here is the most important one. And now, if we replace the expression for the chemical potential in an isothermal system, because when we deal with equilibrium conditions modified by gravity, the system is, by hypothesis, isothermal. And then d mu y is equal to vi dp. This is very important. Suppose that now you want to, let me erase here this arrow, sorry, but now you can multiply both sides of this equation by the mole fraction of component I. So let's multiply it here, and then you may sum up over all the components. Yeah, you may sum up over all the components. Right. When you do that, you have V, the total molar volume, d P, it's equal to the overall molecular weight, right, which is the sum of xi, mi, okay, g, d, z. when you do that, you obtain rho. Right? And this is the hydrostatic condition. And the hydrostatic condition appears automatically when the system is isothermal and in equilibrium. Okay. Well, this is very interesting. It's fascinating, actually. Okay. If you want to know more about compositional grading for both isothermal and non-isothermal systems, okay, get the book, right? Read it. Take a read of it. Send your questions. I'll be happy to answer them. We are preparing a full course coming soon about thermodynamics applied to reservoir engineering. It will be very interesting. Okay? So watch out and stick to us. Okay, you can do a very good job together. See you. Bye-bye.